Today's lesson is going to be similar to lesson 8.5 in that it's not a whole lot of new math per se. It's sort of just a new way to describe things. Just like we did with the angle of elevation and angle of depression, we're just going to look at a new way of describing things that we will then apply our sine, cosine, tangent functions to. So the problems that we do are going to be pretty much the same as we've been doing. We're just going to have a new way of describing the sides and the angles and the things that are involved. So we're going to watch a quick video clip first that I think will maybe, tie this in a little bit to something that you already know. So check it out.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Doing a demonstration. Oh! Ah! Goodness. It's so difficult sometimes to get the arm back inside.
Okay, so obviously we see vector, and he describes a few times exactly what a vector is, and that's what we're going to be looking at, are vectors. And essentially a vector is just a fancy way of describing an arrow. So we have to describe the length of the arrow or the magnitude, as Vector mentioned, and we also have to describe the direction. And that's where the angle comes in. The angle would describe the direction, and the length of the arrow would describe the magnitude. So as we take a look at this, I'm going to come down here and look at the definitions first, and then we'll come back up here and look at adding vectors. So vector, simply put, is just any quantity that has magnitude, which is a fancy word for size, and direction. It has to have both, right? We can't just have one. So if we say, I walked 3 miles, that's not describing a vector. But if I say I walked 3 miles north, then that's a vector. I've described magnitude and the direction. So the simplest way to represent a vector, just like Vector explained earlier, is with an arrow. Right? If you think about an arrow, it points in a certain direction, and it has a certain length. So it has magnitude and it has direction. The magnitude is just its size, or the length, when we're talking about an arrow. Now, another way that we can describe a vector, so one way was just looking at an arrow. An arrow has length, an arrow has a direction. Another way to describe a vector is to look at its initial point and its terminal point. So if I said, I started in one place and I ended 10 meters to the north. I would have my initial point, I would have my terminal point, and I could look at the vector that described that movement. So the initial point is just the point at which you start, the terminal point is the point at which you end. But that can describe a vector as well, right? The vector 10 meters north could be described by showing where I started and where I finished. Now, when we talk about a resultant vector, think about, I'm going to cover up part of that word. What do we have left? Result. So a resultant vector is the result of when we add two other vectors together. So when we take two vectors and we add them up, we get a result. Now, another neat way for describing a vector is using x and y coordinates. If we think about a Cartesian plane, just a basic graph where we have an x-axis, we have a y-axis. If we were to pick a point, let's say we pick a point 2, 3. Okay, we can even, we'll draw a y-axis and an x-axis. And let's say that we pick a point, let's call it 3, 2. So that'd be about right there. There's our point. Now, we could use that coordinate 3, 2 to describe a vector, right? The vector would be starting at the origin, and it would end at that point. So we can use x and y coordinates to describe vectors as well. Now the thing about vectors is that when we use x and y coordinates to describe them, that doesn't necessarily mean that they start at the origin and end at that point. All the x and y coordinates do is it allows us to build the vector, and then the vector can be moved around anywhere in a plane. So if this arrow were here, we would describe this as 3, 2. But we could also move it down here, and the vector would still be described as 3, 2, because all that 3 and 2 describes is the length along this edge here and the length along this edge here, if we were to look at it almost as the hypotenuse of a triangle, which we'll get more into later. So for the time being, just realize that the vector being described as x and y coordinates really just gives us this magnitude and direction, but that doesn't mean that our vector must start here. Our vector can be placed anywhere in a plane and still be described as 3, 2. So when we describe vectors this way using x and y coordinates, the resultant is really simple to find. Because if we have a vector A with x and y coordinates and we have a vector C with x and y coordinates, when we add those two vectors together, we just add their x's and we add their y's. Simple as that. If we want to look at this visibly, let's pick another vector like that. Now, when we're adding vectors as arrows, what we do is we just take one vector, we take the second vector, and we put its tail right at the head of the first vector, right, in a row. And then the resultant vector is actually going to be from the tail of the first all the way to the head of the second. So if we describe this vector, we can take this and move it back in, and we said we described that as 3, 2. So let's write 3, 2 over here, 3, 2. And oftentimes when they use these x and y coordinates, they use these funky brackets instead of regular parentheses. So let's move this other vector over here, and let's say this vector, if this is 3, 2, this looks to be maybe 4, -2, maybe a little less than -2. So let's call it 4, let's call this 4, maybe -1, or a little more, I guess, a little more than 2. Let's call it -2.2, right? That seems a little bit lower than that is high. So then we'll look at our resultant. If we were going to add these based on x and y coordinates, our result would be, when we add the x's, we get 7. We add the y's, we get -0.2. And if we look at this here, we place this at the origin, we can see this vector is at about 7, -0.2. So we can either add vectors by looking at the arrows, or we can add vectors using their x and y coordinates. So when we look at these vectors, the magnitude of vector ON is just its length, right? So that's the distance from O to N. Get my eraser back. So the initial point is O, the terminal point is N, like we talked about before, and so the ordered pair for this would be, well, we can look 1, 2, 3, 4, 5, 2. So we would call that 5, 2. But again, this vector, to describe its length and its direction, we use 5, 2. But this vector can exist here. If it were here, it would be called 5, 2. If it were here, it would be called 5, 2. If it were down here, it would be called 5, 2. Because all 5, 2 does is describe how much we move in the x direction and how much we move in the y direction to describe the length and direction of the vector. It doesn't necessarily describe where it exists in a plane. All right, moving on to our first example. This one, they're just going to have us describe it. It says describe OM as an ordered pair. So now we're getting a little trickier because we have an angle and a length. Right? So this is another way to describe a vector is by giving its angle and by giving its length from, either an angle of depression or an angle of elevation. But in this case, they want the x and the y. They want the ordered pair. So we need to find those two lengths. Well, if we have 80, which is the hypotenuse, and we're trying to find x, which is the adjacent side to that angle 40, then adjacent and hypotenuse, we're going to use cosine. So if we look here, cosine of 40 is going to be the adjacent side, x, over the hypotenuse, 80. Move 80 over to the other side, so multiply both sides by 80. Solve for x, punch that into your calculator, you get about 61.3. And then same thing here, if we're trying to find y, that's the opposite side. So opposite and hypotenuse, we're going to use sine. So sine is going to be y over the hypotenuse, which is 80. Multiply both sides by 80. Punch that into your calculator to get values. So if we're looking at the x and y, since this is to the left, right, it's to the left of the origin, then it's in the third quadrant, so both coordinates are going to be negative. This is to the left of the origin. This is below the origin. So to the nearest tenth, which is what they told us in the directions, negative 61.3 and negative 51.4. And again, notice these brackets as opposed to parentheses whenever you're writing a vector. That's how we know that this is a vector and not just a point on a graph. All right, example 2. Now we're putting this to use in a word problem. It says a boat sailed 12 miles east and 9 miles south. The trip can be described by the vector 12, negative 9. Use distance and direction to describe this vector a second way. So in the previous example, they gave us the angle and they gave us the length, right, to describe the vector, and they wanted us to find the x and y coordinates. Here, they're giving us essentially x and y coordinates because they say it went 12 to the east and 9 south, so we can describe it this way. Now, instead, they want distance and direction. So they want to know the length of this hypotenuse and the angle of depression here from east. So if we're finding the distance, if we have 9 and 12, we can just use Pythagorean theorem. Right? They say the distance formula, but essentially this is just Pythagorean theorem, where we've got two legs of a right triangle. So you get 12 and negative 9, square them, you get 81 and 144, square root of 225 is 15. So this length here is going to be 15. Now we need to find the angle. We have these three lengths, but we need to find the angle. And if you hadn't figured this out yet, this is a 3, 4, 5 triangle. So you could have done this without doing any of this distance formula, right? Because 9 is 3 times 3, 12 is 4 times 3, and 15 is 5 times 3. So we have a 3, 4, 5 Pythagorean triple. So we could have done that without any work. Now, if we're going to try to find this angle, typically when you do this, try to use as much information as they've given you. You could use cosine and use 12 and the value, that 15 that you found for the hypotenuse. You could do sine and use 9 and the value that you found for the hypotenuse. But typically what you want to do is you want to use the values that you're given to begin with. Just in case you made a mistake here, you don't carry that mistake over into another portion of the problem. So if we set this up, we have 9 and 12, which are opposite and adjacent sides. The trig function with opposite and adjacent is tan, right? Tangent, SOHCAHTOA. TOA is opposite over adjacent. So opposite is 9, adjacent is 12. In this case, we get 0.75. Again, when we have this, our variable is in the trig function. In order to solve for it, once we get this far, we have to use inverse, right? Inverse tangent to solve for the actual angle. Punch that into our calculator. We get 36.86 and so on. So the boat sailed 15 miles at about 37 degrees south of east. And again, 37 degrees south of east, we started east and we go south. So we're describing this angle in here. One more example and then we're done. As we look at these, now they're going to have us add vectors like we talked about before. We've got two vectors, 4, 3, and 4, negative 3. So notice how one goes this way, one goes this way. So they show them here, write the sum of the two vectors as an ordered pair, then draw S and the sum of V and W. So notice it says to find the first coordinate, we're going to add the coordinates of V and first coordinates of V and W. So the first coordinate of V is 4, first coordinate of W is 4. We're going to do the same thing for the second coordinates, 3 and negative 3. So 4 and 4 make 8, 3 and negative 3 make 0. So the resultant vector of those two, when you add them together, should be 8, 0. Now if we're going to draw these, typically we'll start at the origin, right? So the first one would be 4, 3. We already have that here. The second one would be 4, negative 3. That one goes down. And then the value that we found for this was 8, 0. So I'm going to draw this as a dashed line, but that would be just a horizontal line along the x-axis going out to 8. Now, if we take these and we add them the way that we talked about adding vectors, here they show that in this bottom figure, but I'm going to move these down to show. So we take the first one, and it doesn't matter what order, right? We can take the first one and the second one, put them together, and the resultant should be from the beginning of the first to the end of the second. Now, once again, it doesn't matter what order. We could have taken this one first, right? So if we start here, we take that one first, and then take this one second, we still get the same answer. Okay? So it doesn't matter what order you add vectors, you're always going to come up with the same answer. So here it says we draw the resultant vector from the initial point to the terminal point, and that's what we did here. From the beginning of the first to the end of the second, we get the same result as if we were to add these using the component parts or the x and y ordered pairs. All right, give the quick check a try, and we will continue to work with these. Vectors is a big topic in IB math, so it's definitely something that we want to get at least a little bit of an understanding for.